Hello and welcome to this video on the derivation of the SUVAT equations. The SUVAT equations are something that you'll probably be introduced first to at Physics A-level and are included in the Maths A-level course as well. And they are really quite simple. They give you a basic idea of a few things such as displacement, initial velocity, final velocity, acceleration and time, given that the acceleration is constant. So with that being said, let's jump into the first SUVAT equation. Number 1, v equals u plus a t. Now most of these can be derived from a simple velocity time graph, and that's what we're going to draw for this one. So if we have velocity on the y-axis, time x-axis, and we draw a straight line, constant acceleration, we can mark onto this graph the initial velocity, which will be the y-intercept here. And we also know that the final velocity is going to be here, which will be at v. Now the time taken for this will be t. So if we want to find the gradient of this line, what we can do is say that the gradient is equal to the difference in the y values, so that's v minus u, over the difference in x values, which is just t. Now we also know that the gradient of a velocity time graph is equal to acceleration. So m is equal to a, so this just equals a. So a equals v minus u over t, or if you rearrange it, v equals u plus at. Now you can see that this follows the same form as y equals c plus m x. And that's quite easy to see from the graph, as m or a is your gradient and c is your y-intercept, which is u. Moving on to equation number 2, we have s equals a half u plus v times by t. Now we know that a property of a velocity time graph is that the displacement travelled is equal to the area underneath it. So if we consider this shape here, we can see that this is a parallelogram, and the formula for the area of that is a equals a half a plus b h, where h is the height of it and a and b are the sides, parallel sides of it. If we sub in so that we know the area underneath of this is going to be equal to displacement, so we simply have displacement equals a half brackets this side here, which is going to be u, this side here, which is v, and then this side here times by t. Now the rest of the equations can be derived just from these two, and we're going to start off with s equals ut plus a half at squared. You can get this formula from subbing this formula into this one. So if we start with equation 2, where we have s equals a half u plus v t, we can sub in for v. So eliminating v, we get s equals a half u plus at times by t. If we expand all of this, so 2u plus at times by t, we get s equals u times by t plus a half a t squared. And we can also do the same, but subbing in for u instead, and we'll get s equals vt minus a half a t squared. If we eliminate t from this equation by subbing in t equals v minus u over a, we get s equals a half u plus v times by t, which is just v minus u over a. Get s equals a half u v minus u squared plus v squared minus uv over a, get 2as is equal to, those two cancel, so you get v squared minus u squared, so v squared is equal to u squared plus 2as. Now these are all the SUVAT equations that you need to know. You can also derive these last few using calculus. I'm going to show you just how to do that now. If we take v equals u plus a t, we know that the displacement travelled is going to be equal to the integral of v with respect to time. So s equals integral of v with respect to time. If we sub in for v, we get s equals the integral of u plus at with respect to time. And since u and a are constants, so they're not going to change, they're not functions of time, we can just simply integrate them so that we get ut plus a half at squared plus c. Now we know that the distance travelled when t equals 0 is going to be 0. So if we sub in for 0 equals 0 plus c, therefore c equals 0. Therefore we have s equals ut plus a half at squared. Now we can do the same if we use the fact that a is equal to the rate of change of velocity, dv by dt. Now dv by dt is also equal to dv by ds times by ds by dt. And you can see that it's the same sort of thing, that ds is cancel. We also know that ds by dt is equal to v, so we simply have a equals v dv by ds. If we separate and integrate, we get the integral of a with respect to s is equal to the integral of v with respect to v. Therefore we get as equals a half v squared plus c. We also know from our velocity time graph that when the displacement is 0, v is equal to u, which is shown here. When it's travelled no distance, the time is 0, and so v is equal to u. So if we sub that in, we get 0 equals a half u squared plus c. Therefore c equals minus a half u squared. Subbing in again, we get as equals a half v squared minus a half u squared. Therefore v squared equals u squared plus 2as.